In today's episode of Supervolcano Mythbusters, we are going to separate fact from fiction and find out what really makes a supervolcano. Hi, I'm here with the U.S. Geological Survey. This is a production of the Cascades Volcano Observatory in the beautiful Pacific Northwest. We monitor volcanoes and tell people about them so that communities can make informed decisions about living with volcanic hazards. But sometimes the truth about volcanoes isn't quite what we expect or even what we want to hear. So this series, Supervolcano Mythbusters, helps us explore some of the misconceptions, myths, and urban legends that surround some of the world's most famous, potentially large, explosive eruptions. But first, what makes an eruption super? The term supervolcano was coined in 1980 by a geologist named Howard Wood. He actually meant it to describe the potential for certain large lakes to drain catastrophically. But since then, the term has been applied to any volcano capable of an eruption magnitude 8, on the Volcanic Explosivity Index, or VEI. For reference, a VEI 6 magnitude eruption is about as big as an eruption can get, while still being considered a normal eruption. A VEI 7 eruption is considered a major eruption, such as Mount St. Helens in 1980. And a VEI 8 eruption is truly catastrophic, like the eruption of Mount Pinatubo in the Philippines in 1991. An eruption at this scale would require the simultaneous collapse of the upper portion of the magma chamber and the overlying structure, leading to the formation of a caldera. In the case of Mount Pinatubo, the caldera formed after the eruption was over, and in the case of Mount St. Helens, the caldera formed before the eruption. Caldera-forming eruptions can also be considered supervolcanic, but they are much less common than caldera-forming eruptions. So how big is a supervolcanic eruption? To answer that question, we turn to the VEI, which describes 8 different eruption magnitudes ranging from explosions that are too small to see all the way up to the largest imaginable explosions. Each whole number on the index represents an order of magnitude increase in terms of eruption volume, and an even greater increase in terms of eruption explosivity. When describing the magnitude of an eruption, we use the term erupted volume, which refers to the total volume of all the material erupted during an event. For example, the 1980 eruption of Mount St. Helens had an estimated erupted volume of about 2.6 cubic kilometers. That's about 1.6 cubic miles. By comparison, the 1991 eruption of Mount Pinatubo had an estimated erupted volume of around 4.8 billion cubic meters, or about 1.8 cubic kilometers, or 0.7 cubic miles. Now let's take a look at what the VEI says about supervolcanoes. It tells us that a supervolcanic eruption, a VEI 8 eruption, requires an erupted volume of more than 1,000 cubic kilometers, or 386 cubic miles, and that's a huge amount of rock. Let's put this into perspective by comparing it to one of our local volcanoes, Mount Rainier, in Washington state. Even though Mount Rainier is one of the most dangerous volcanoes in the United States, it's not a supervolcano because its magma chamber is not big enough to hold more than 1,000 cubic kilometers of magma. Its magma chamber is about 500 times smaller than this, holding only about 2 cubic kilometers of magma at most. In fact, the largest historical eruption of Mount Rainier was about 170 cubic kilometers or 66 cubic miles, which is less than 20% of what it would take to earn the title of supervolcano. There are only a handful of places on Earth where an eruption that size could happen. Some of the best-known supervolcanoes include Yellowstone National Park in the United States, Lake Toba in Indonesia, and Valles Caldera in New Mexico. These locations have magma chambers that are large enough to produce a VEI 8 eruption. The relevant size threshold for these magma chambers is about 2,000 cubic kilometers or 770 cubic miles. That size is thought to be necessary to provide sufficient volatile content and therefore explosive potential to trigger a VEI 8 eruption. Here in the Pacific Northwest, there are no volcanoes that meet the size criteria to be considered a supervolcano. Our largest volcano, Mount Mazama, which underlies Crater Lake in southern Oregon, had a maximum magma chamber size of about 70 cubic kilometers or 27 cubic miles, which is about 1% of what it would take to produce a VEI 8 eruption. What might surprise you is that there are many places on Earth that have experienced eruptions that were technically supervolcanic in size. But because their magma chambers were not large enough to contain that much magma, these eruptions did not form calderas. They are known as supereruptions. Many supereruptions leave behind evidence of their massive size, such as the 1783 Laki eruption in Iceland, which ejected 15 cubic kilometers of ash into the air. That's about 6 cubic miles, or nearly 10 times the volume of the 1980 eruption of Mount St. Helens. Volcanoes that produce super eruptions are generally categorized as ultra-efficient systems because they are able to produce enormous eruptions without building up large magma chambers. On the flip side, volcanoes that produce caldera-forming eruptions are generally categorized as inefficient systems because they must accumulate large volumes of magma before a caldera forms. It's important to remember that the term supervolcano is used to describe both caldera-forming eruptions and caldera-forming eruptions. Despite this, I think it's clear that not all large eruptions are created equal. The size of the magma chamber plays a critical role in determining whether an eruption will form a caldera and how large the eruption will be. If you thought this cleared up the confusion around the term supervolcano, then I have some more news to share with you. Scientists don't actually agree on whether an eruption can be considered super simply based on its volume. Instead, many prefer to define a supervolcanic eruption based on its impact on the surrounding landscape. When discussing the formation of large explosive eruptions, scientists talk about two different types of collapse: viscous and gravitational collapse. Viscous collapse happens when the viscosity of the magma increases so much that it prevents gas bubbles from escaping. As a result, pressure builds up until the rocks around the magma chamber can no longer support its weight, and the chamber collapses. Gravitational collapse happens when the weight of the overburden causes the rocks above the magma chamber to fail. This type of collapse is more likely to occur when there is a significant amount of water present. Whether a large eruption will form a caldera depends on the relative timing of magma withdrawal and the collapse process. If gravitational collapse occurs first, then the eruption will produce a caldera. However, if viscous collapse occurs first, then the eruption won't produce a caldera. At a minimum, a VEI-8 eruption will either totally or partially destroy the pre-existing structure, resulting in a caldera. The size of the caldera that forms during a supervolcanic eruption can vary widely depending on the size of the magma chamber and the amount of material erupted. For example, the youngest supervolcano in the United States is Long Valley Caldera in California. During the Holocene epoch, which began about 11,700 years ago, it produced an eruption that was about twice the size of Yellowstone's 1985 eruption. Yet the Long Valley Caldera itself is only about 10 kilometers or 6 miles across and 30 kilometers or 18 miles long. That's about the same size as Crater Lake in Oregon. On the other hand, the youngest supervolcano in the world is Taupo in New Zealand. During the Holocene epoch, it produced an eruption that was about 3 times the size of the 1815 eruption of Mount Tambora in Indonesia, the largest eruption in recorded history. Yet the Taupo caldera is 28 by 35 kilometers or 17 by 22 miles. That's about the same size as Mount Rainier in Washington state. The bottom line is that an eruption doesn't need to be supersized to be super. Whether a caldera forms during a large explosive eruption depends on the timing of magma withdrawal and the collapse process. Eruptions that withdraw magma fast enough to prevent gravitational collapse will produce enormous ash clouds, but not necessarily a caldera. Eruptions that withdraw magma slowly enough to allow gravitational collapse to occur first will produce calderas, but not necessarily enormous ash clouds. The true super eruptions are those that manage to do both. We know that large explosive eruptions can have enormous impacts on the biosphere, but just how much impact depends on a variety of factors, including the efficiency of the eruption and the distribution of ash and other fine particles. In my next video, we will compare the hypothetical impacts of a caldera-forming eruption versus a caldera-forming eruption to find out which one would be worse. In the meantime, please stay tuned for future installments in the Supervolcano Mythbusters series. Thanks for watching.